The thing that we have to remember about the hypergeometric distribution is that it's extremely similar to the binomial. There are only two options. Um, the number of trials is fixed, but the one difference between hypergeometric and binomial is binomial you need to have independence, and hypergeometric is when situations are dependent on each other. Okay, so here we've got this is really going to just basically break down to some of our counting problems that we've been doing. Okay, here you've got an example. You've got a hung jury. Okay, suppose there is a pool of 25 jurors, and they'll randomly select 12 of them to see what the verdict is going to be. Basically, 23 of the jurors have been convinced that somebody's guilty. 2 of them still believe the person's not guilty. Okay, so here we're wondering about the probability of having a hung jury or having a non-unanimous jury. Okay, so here I'm going to let X be a random variable. It's the number of jurors who vote not guilty. I know that there are 2 out of the 25 that are going to vote not guilty, but I'm only selecting 12. Okay, so I could select 0 of the non-guilties, I could select 1, or I could select 2. Notice in this case there are 2 options, guilty or not guilty, and the number of reps is known. It's just going to be 12, or actually the number of reps is 25. There are 25 people, but I'm going to select 12. But the thing that's different between this and a binomial is that I only have a limited amount of people to select from. So every time I make a choice, I'm also making a choice. Every time I make a choice of what to pick, I'm also limiting the options I can pick from. Okay, so this is by definition dependent. Okay, so here, if I have a hung jury, that means that the probability of X, which is the number of jurors who vote guilty, or sorry, not guilty, will be at least 1. Okay, so if I get one of the guys that's going to vote not guilty, or if I get both of them, either way will result in a hung jury. Okay, so this is actually X here, the number of jurors who vote not guilty is a hypergeometric situation. M, Minitab calls it M, I call it R sometimes, textbooks call it R. This is the total amount of successes, okay, or the things that we're interested in, or the thing that we've actually defined our random variable here. We've defined our random variable as the not guilties. The total number of not guilties is 2. Large N is the total number in the whole pool. There are 25 in total. And little n is the number that I'm selecting. It's the sample size here. So I'm only selecting 12 out of the 25 people. Hung jury, as I said, would be X is anything greater than or equal to 1. I can do this then by just calculating what the probability of one not guilty is, plus the probability of both not guilties, or I could do the complement. This is 1 minus X is less than or equal to 0. Okay, so here's 1, here's 2, the complement is 0. Okay, so here this is just going to be not guilty votes. Out of the 2 of them, I'll select 1. Guilty votes, out of the 23, I'll select 11. Out of the total 25, I select 12. Okay, so this is 1 member of the random selection being not guilty. Here is both being 2 in the 25 being not guilty. Okay, so 2 choose 2 times 23 choose 10. Okay, so I could do this by hand, or of course I do 1 minus exactly 0. That's 1 minus 0 not guilty votes, and I get something about 0.74. Let me also show you, of course, how to use Minitab to do this if you want. Under Calc, probability distribution, this is the hypergeometric distribution. Here I want the cumulative probability. I want less than or equal to 0. Or it's similar to saying, I mean, if I did less than or equal to 0, it's the same thing as X is exactly 0. But so it's fine if you put cumulative probability. Large N, the total number is 25. the number of people who have not guilty votes is 2, and the sample size is 12. I want less than or equal to 0. Okay, so here I get 0.26. 1 minus 0.26 gives me this 0.74. Okay, we can also talk about the expected number of not guilty votes. Okay, this is the formula for the hypergeometric expected value, R, or if you like, capital M over N times by N. Okay, so there's 2 votes out of the 25 that are not guilty, and multiplied by the number of selections, I expect 0.96 of a guilty vote. Okay, so 0.96, very close to 1, so I'm expecting about 1 guilty vote. What about the variance? A little bit more of a complicated formula for the hypergeometric situation. Just sub in the values that you need and just plug them into your calculator. The variance is 0.478. If I want the standard deviation, I'll take the square root of that variance, so I get about 0.7. So what I'm saying here is I expect almost 1, give or take about 0.7. So anywhere between 0.3 of a not guilty vote and 1.7 of a not guilty vote. Okay, so you can see not only if I expect it or not, but what the range is. So really I would expect, I think this is saying that normally you would expect to have at least, you'd expect to have a hung jury, considering that the believable range is between 0.3 and so somewhere around 0 and somewhere around close to 2 not guilty votes.